are into Unit 9. Lippy's favorite unit. Today's not bad. The next couple days aren't bad. And then we get into redox and electrochem and that sort of thing. And then that gets a little more painful for me. But we'll get through it. We'll get through it. We will. All right. So we're talking about thermodynamics here. And you guys are familiar, I think, with this idea. The first law of thermodynamics, energy cannot be created or destroyed. Total energy of the universe is constant. However, you can convert from one form to another. So we can take energy stored in chemical bonds, turn it into heat energy. We can take energy stored, or heat energy from the environment, store it in bonds. We can take, a mechanical energy and store that as electrical energy. So there's lots of different things that we can do. We can convert it, but we just can't create it or destroy it. Okay? So a lot of our energy actually comes from sunlight. If you trace it back and go back into that. But remember, that's coming from the nucleus, where the two hydrogen atoms on the sun are fusing and creating helium.
Hello.
Hey.
Hello.
Hi. And so that there's actually some of the mass from that material being created and converted into energy, and that's your E = mc squared guy. So yeah, it can't be created or destroyed under normal conditions. Okay, fusion and fission are not really normal conditions. So kind of take that with a grain of salt. Just remember that there is that whole nuclear side, which we really don't get into at all in AP Chem, but is a fascinating kind of world if you want to get into that sort of material. So enthalpy, we've talked about that. We talked about that back in, I believe it was Unit 6. We talked about delta H. Do you remember we talked about bonds breaking minus bonds formed? Figured out what was exothermic, endothermic. So we've dealt with delta H, okay? And that tells us where the energy is coming from or going to during a reaction, okay? For example, if we have an endothermic, exothermic, is it getting exchanged with the surroundings? Is it coming from the surroundings? But it doesn't give us insight into whether the reaction will actually happen or not, okay? So, for example, if we have hydrogen and nitrogen or oxygen in the air, okay? They can be explosive, right? I mean, well, oxygen isn't explosive, but hydrogen's explosive. Oxygen supports combustion, okay? So the oxygen, isn't explosive, but these two together, the oxygen supports the combustion of the hydrogen, and you can get an explosion. That's what I'm trying to say. Hydrogen and oxygen are both present in the atmosphere. So right now, in our atmosphere surrounding us, we've got both of those. But if I light a match here, okay, this room isn't going to explode. Thankfully. Okay? So enthalpy isn't just, all of it. There has to be some other stuff there. Okay? And that's only one part of the puzzle. Okay? Now let's look at entropy kind of closely and related, and this is not in your packet. Okay, this slide I added in today. I was thinking about this and I'm like, I really should go into this, especially if you get into college further. You're going to kind of not be happy with me if I don't go through some of this idea. Okay, so entropy is related, and that's what we're going to talk about. Entropy is related closely to degrees of freedom. Okay, so when we talk about entropy, typically kind of the generic or the easy way out to talk about it is to say it's how much disorder exists, okay? How much randomness exists in a situation. And that's kind of the cheating way of doing it, all right? For example, I could say, look at my desk. I came in this morning, Alex left this desk perfect. There was nothing on it. Now look, entropy has taken over. Disorder has occurred, okay? And systems they say, tend to go to chaos or tend to go to this disorder, okay? In reality, what they should say is they tend to become more free or distribute themselves evenly, okay? So energy, for example, okay? I don't know what's booming. I think it's somebody showing a movie because it's not thunder.
Or it's the wind.
Oh, it could be the wind. Oh, very good. Yeah, I have not been outside since I came in at 6:30 this morning. I don't look back. My update on my computer started at 6:45 and didn't get done until 9:45. Been a rough day, technology-wise. Anyway, so degrees of freedom are how we see that. So when we talk about energy, for example, okay, your mom always yells at you, don't hold the door open, you're letting the cold in, okay? You're not letting the cold in, you're letting the heat out. Now, don't tell her that because she'll probably backhand you. But the truth is that that's what you're doing because the energy, the heat energy, is dispersing itself. It's spreading out as far as it can. And that's what happens here, okay? So in ice, for example, when we talk about ice, you've got your water particles, and they're locked in there. They're not moving. They can vibrate, but they're fixed. They're not able to move beyond that fixed position, okay? They can vibrate, and as it gets hotter and hotter, they're able to vibrate more to the point where eventually those intermolecular forces will allow it to transition, and then you have your liquid, okay? So you're increasing that level of freedom, so to speak, and they're able to move through that. Now, these levels of freedom that they talk about microstates. So how many places can these things go? Well, when they're locked into a solid, they can't go very far. They can't do much, okay? When they're a liquid, though, they can translate and move, so they have more areas of freedom. So they call that microstates, okay? And then as we continue to heat it up, eventually we get rid of the intermolecular forces. We end up in that gas section here. They're able to translate, rotate, the hydrogen bonds are dispelled, like gone. And so because of that, they have more degrees of freedom, which means that they have higher entropy, okay? So kind of think of it in terms of these microstates, this area of freedom, versus just this randomness or disorder, okay?
So like a solid has less entropy than a liquid. Liquid has less entropy than a gas.
Yep. Okay. Exactly. So when we look at these, we're going to eventually get to something in this packet called Gibbs free energy. And Gibbs free energy consists of 3 components, okay? And it's going to determine if a reaction will actually happen on its own, okay? Or if we would have to introduce more energy in it to make it happen, okay? So electroplating, which we'll get into way at the end of this unit, is an example where normally that would not occur, but if we add electricity in, add more energy in, it allows for that process to happen, okay? So Gibbs free energy is a calculation that we're going to do that involves 3 components. One of them is enthalpy, which we talked about in Unit 6. One is entropy, which is what we're talking about here. Measure of randomness, or this measurement of these microstates. And then also temperature is the other component of that. Okay, so that there's 3 things that are involved in that calculation. So the changes in all of these will play a role in determining the spontaneity. We don't like to use the word spontaneity. We use the word thermodynamically favorable. So I talk about spontaneous here, but they don't like that in AP land, okay? They like thermodynamically favorable. So you will hear me using that more. I get you to think of it in terms of spontaneous because it happens without extra intervention. For example, that ice in your cup, okay? Over time, if it's sitting out here in the room, what's going to happen to it? It's going to melt. It's not going to form into more ice, is it? Okay? So that is thermodynamically favorable to occur, as opposed to it turning into ice, which is not. Now, if I put it in the freezer section of this, then the opposite will occur, because we changed the temperature. We've changed, components about it. Okay? But they like the thermodynamically favorable. Now, why? Why do they like thermodynamically favorable versus spontaneous? Okay? Well, because if you're talking about like the running boards on my truck, okay? My truck's 10 years old. What do you think is starting to happen to those running boards in Wisconsin with the salt and the weather we have? Right, they're rusting, okay? Did that happen the second that those running boards were created? No, it's taken time. But, so it's not in terms of what we think of as spontaneous. Okay, when we think of the word spontaneous, we think, boom, happened, okay? In chemistry land, when they talk about spontaneous, they mean happening without external intervention. Okay, so that rust in chemistry land is spontaneous, but it took a long time to happen. Okay, so you got to kind of think of it in terms of where you're at. So on the AP exam, they don't like you guys to use the word spontaneous. You might hear spontaneous if you go off to college. So that's why I like to still sprinkle it in here and there and like to talk to you about in chemistry world what that actually means. Just like organic. When we talk about organic in chemistry land, we're not talking about, a certain section at Woodman's that you get your food, okay, that hasn't had fertilizers, pesticides, blah, blah, blah on it, okay? What we mean is something that has carbon-hydrogen bonds and, that sort of thing. Okay, because in chemistry world, we have different definitions of things, okay? And spontaneous is another thing that's like that. All right. So like I said, spontaneous, or scratch that out and put thermodynamically favorable, because I want you, especially if you're taking that exam, I want you to get used to writing that word. Thermodynamically favorable processes proceed without outside assistance or intervention, okay? They're going to proceed until they reach equilibrium. Spontaneity is not related to speed, how fast something happens. Okay, graphite will turn into diamond given enough pressure and time.
You're telling me I could turn my graphite pencil into diamonds?
Not in your lifetime.
But
Well,
if I let it,
well, then it wouldn't. It ends up being like cubic zirconia or something like that. It's not. Yeah. So again, not in your lifetime. But yeah, I mean theoretically, yes.
it's just going to be over a long period.
Yeah. Okay. But it'll happen. It's spontaneity. It's spontaneous in chemistry. Thermodynamically favorable. But yeah, not in your lifetime. So the process, well, I think they are doing some in the labs, to be honest with you. But great deal of pressure and that sort of thing.
What about that? I remember seeing a video on that.
Yeah.
Where they make diamonds in a lab now.
I think too, and I could be wrong, but I think you can take people's cremains and make them into like diamonds and stuff like that now.
That's like kind of cool.
It's kind of cool, kind of creepy,
weird.
kind of cool, kind of. Yeah, I know. Like when my sister passed away, she was cremated, and I got some of her cremains, and they're still sitting in a Ziploc bag in my office. Like I don't know what to do. It's like I have.
But it'd be cool to turn that into like a weird,
I've thought about it. They do sell like little. You can like buy little vial things that you can put on a necklace that you can put. And I'm just like, I don't know. I'm still. Oh yeah, I have the dog stuff too, but But I mean, this is my, you're like,
Yeah.
it's like, I just, so
Maybe my
yeah,
dog, but not.
I need to still like try to figure out what I got. Yeah, it's still sitting in the Ziploc bag though, so I know where it is.
Yeah, at least you didn't lose your.
And I was also,
Yeah.
I've seen like companies and stuff where they make like decorative glass
Right, yeah.
Cousin
like
got that
pictures
done.
that you can fill with.
Yeah,
color.
well, I only have a little, like, her son's kept,
Yeah,
and
no,
then we
they're only
spread
like-
ashes,
yeah,
like,
yeah,
at the
yeah.
beach and stuff, so there's, but yeah,
They're small.
illegally, I'm sure, now that this is gonna be on YouTube. So I won't mention what beach. But, because it could have been a private beach that we own, I don't know what the legality of it is, but yeah, anyway, I know there's something about spreading ashes like you're not supposed to. Anyway, it's, yeah. But yeah, there's certain things that you can do with that, anyway, we digress. So spontaneous versus, processes that are spontaneous in one direction are non-spontaneous in the other. Now we can sometimes get them to go the other direction. Like I said, sometimes we can add energy in or take energy out. Yeah, like with the ice, we can change that by altering the amount of energy that's being input. And so yeah, the ice is a good example of that. What else was I thinking? Oh, the electroplating, which we'll get into when we get into like batteries and stuff like that. So we'll talk about electroplating, and that's how they make some of the costume jewelry to be like, they have gold electroplating on it, where it's one metal underneath and then it's got a layer of like gold that they've so the whole thing is gold, but they've got the top layer is, so it looks nice and cheaper. So, so spontaneous, here, if we have like gas here and nothing here, it's gonna become equilibrium, but it's not gonna go back the other direction. Okay, so this is not gonna end up taking this and becoming nothing. Eggs, spontaneous, you drop them, they're gonna break. Now, in theory, could we put that egg back? I guess possibly, but the chances of that happening are pretty slim, okay? Humpty Dumpty sat on a wall. Yeah, they just couldn't, all the king's horses, all the king's men, couldn't put them back together again. Please tell me you guys know those.
Mhm.
Okay. It starts to scare me sometimes when I realize that I'm getting old. All right, so temperature and pressure can affect this spontaneity, okay? So for example, if we have ice, okay, temperature is greater than 0, it becomes water. Take that down, you can change it, okay? And we're going to look at that. There's going to be a chart that you guys, especially those of you who are taking the exam, are going to have to memorize. It's not bad, but it's very, very helpful, okay? All real processes are irreversible. The reverse of any spontaneous process is the non-spontaneous one. So like I said, that's not going to become ice sitting out here at room temperature. Non-spontaneous processes only occur if the surroundings do work on the system. So right now the ice is melting. There's work being done. Any spontaneous process is irreversible. And if we return the system to the original condition, the surroundings will have changed. Second law of thermodynamics has to do with entropy. Okay, so process is considered spontaneous if it leads to an increase in disorder or an increase in microstates. So entropy is a measure of randomness or disorder, greater number of microstates. Nature favors this greater number of microstates or disorder.
Right. So,
Like my desk.
say for like the ice, if we put it in the freezer and it freezes, would that be considered spontaneous, even though it's causing less entropy?
Right, but we've got to get to Gibbs. Give me time. Okay.
Okay.
We've got to do work to make that happen, by the way. Okay. That's why you have to plug your refrigerator in.
Oh, okay.
Right? I mean, work is being done on that system to make that happen. At this temperature, that's not going to happen.
I mean, what if it's, stuff? And then,
Well, you would have to take it outside, and then the temperature would be
What if it was
changed, the heat
always
energy would be
outside?
changed, and then,
what if it was always outside, or like a lake?
yeah, but first of all, it's not a closed system. Second of all, the enthalpy, the heat is going to change. So that's changing, and your temperature.
Oh.
Okay, so because of that, it's going to flip it to a non-spontaneous. Yeah, so you've got to let me get the whole picture. Okay, we're not there yet. We'll get there.
Yeah.
Okay, I don't know that we're going to get there today, but we'll get there. Okay. All right, entropy then increases as number of microstates, like I was talking about, these single possible arrangements of positions and kinetic energies increase. So volume, more positions are possible if we increase the volume. More positions are possible for the molecules. They're able to disperse more. Temperature. If our temperature increases, then they're able to go faster. They're able to move and have a greater distribution based on those molecular speeds. And there's a more possibilities for your kinetic values. And then the number of particles moving around. Okay, solids have more regular structure than liquids, so liquids are more disordered. So liquids have more. Well, no, they have more entropy. Okay. Okay, and we'll get to the thermodynamically favorable soon. Okay, maybe not today.
Maybe once.
So melting, is that going to increase entropy or decrease it? Increase it, right? Because it's going to
have more disorder.
Right. Okay, freezing.
Or decrease.
Decrease, because it's going to put it into fixed positions, right? Boiling.
Increase?
Mm-hmm.
Because it's vapor.
Yep, turns into vapor. And then what about condensation?
Increase. Or no, decrease because it's going gas to liquid.
Gas to liquid, right? Does that make sense?
Yeah.
Okay. All right, so hydrogen and oxygen. Did I give you the cheaty stuff? Did I give you all the answers on your sheet? I was afraid I did. Now, look at the board and don't look down. Hydrogen and oxygen combine to form water vapor as a gas. Okay, so we've got hydrogen, we've got oxygen, and then here we've got water.
That decrease it because they're combined.
Right, we've got, and check your paper, I think that's right. Okay, good. I'm still in Cancun brain, so you've got, and this is something where you can kind of look at the moles here. You've got 2 moles, 3 moles on this side, and over here you've got 2. So it's become more ordered. Does that make sense?
Oh.
You've taken 3 moles of material here and combined them into 2 moles.
Okay, yeah. That doesn't sense.
So if you think of it in terms of microstates, here you've got 3 things, here you've got 2. So this is more ordered than this would be.
So lower number means more ordered. Or lower moles.
Here you've got 1 mole, here you've got 2, and we've gone from a solid to aqueous. So there's 2 things here that have changed, okay? Here it was locked into that solid phase, And now as aqueous, it's able to move around and transition more. Increasing temperature. Oh, goodness. I'm ready for my afternoon nap. Been getting one pretty regular, like, you know.
Increasing temperature. Would that increase entropy?
Yeah, because it's going to move around faster. So it has a better chance of, you know, a higher distribution of being in different places. That makes sense? Versus moving around slowly. Afternoon nap too, don't you? Oh, I'm sorry. When I wore contacts, I used to have saline, but probably can't give it to you anyway. Anyway, here we go. Now, there's a couple things here that you can look at to give you clues. Give me one of them. The moles. So here we've gone from 9 to 12. What else?
Also liquid and solid. Yeah.
Right. Okay. So those two things would indicate that we have an increase in entropy on this side. Here, we've only got one thing changing, but decrease. Very good. And here, increase in entropy. Good. Makes sense? Easy way to see it? Okay. All right. Sorry about giving you cheaters there. I think I do that a couple times. I realized that as I was going through this, like I said, the thing was updating. I got partway into like third hour, and I finally was able to access my computer again. And I'm like, I've got to print these out. So I printed them out, and then I started reviewing them. I'm like, oh, shoot. All right, entropy. One might assume that a reaction with a negative delta H, so losing energy, would always proceed since the products have a lower enthalpy than the reactants and are more stable. However, that's not necessarily so. If a reaction has a very high energy of activation, so activation energy, then it will not occur, and it's described as kinetically stable or under kinetic control. So if we have to input a lot of energy to kind of kickstart it, then sometimes it doesn't happen, even though it has a negative delta H. Sorry. In these circumstances, it is possible that a reaction that one might predict as being highly likely produces little or no products. So an example is the oxidation of ammonia by oxygen to produce nitrogen monoxide and water. The delta H is a negative 909 kilojoules per mole, showing that it's very unstable. But the reaction doesn't proceed due to the high activation energy. You would have to input so much stinking energy into it to get it started that we just don't see this happening. Okay, it just doesn't occur. Another example that we assume that a reaction with a positive delta H will never proceed since the products have a higher enthalpy than the reactants. However, some endothermic reactions do proceed. For example, we have, what was that? Probably water? I guess that should be water. Yeah, so we're just taking that and putting it in water. Okay, since this is this reaction, there's an activation energy that must be obtained before the reaction proceed. We can say that the delta H and the activation energy are not the only factors that make this happen. So this potassium chloride has a positive value here, okay? So typically we would not think that this happens, but we know because, remember, we had to memorize our solubility rules, right? Potassium is one of the things that's always soluble. Remember that? So we know that this is going to be soluble. So there has to be something else at play here. Something else is going on behind the scenes that we're like, isn't just enthalpy. Okay, and that's where we're going to bring in this entropy in just a second. Okay, so we're going to bring these together. we can see that when we dissolve this, okay, we're changing it from a relatively ordered state, that's your solid, into a less ordered state as a solution. So that's showing that we're increasing entropy. Our entropy is positive here. So in the reaction here, where we're talking about with this potassium chloride, an increase in entropy is going to allow us to have this reaction occur. So it's not just the enthalpy, the heat, that's at play. It's also the entropy. Okay, so if we had some of that KCl and it was at absolute zero, which we can't get to, but we're close, we would say that its entropy is zero. Okay, that's to say that it's completely organized, it's very ordered. The absolute entropies of substances in the real world, not at 0K, are measured relative to that, and as such have values that are greater than zero. So entropy is always going to be greater than zero. And that makes sense. You guys know what absolute zero is, right? It's where all molecular motion stops. Okay, so nothing in the real world is going to be at that point. So the state, temperature, number of particles, and volumes of the gases are important for that entropy. So you have to be able to look at the state of matter when you're dealing with this entropy. And so when we look at the charts, and I gave you a chart a while back that was like a stapled piece of paper. It had enthalpy values on it. Do you remember that? Enthalpy of formations, I believe it was called. It was stapled. It was an appendix that I had run off. Appendix C, I think it is.
It might be in the room. Do you know how long ago you gave it to us?
It would have been unit 6, I'm guessing. So at the end of first semester.
I don't think I've taken this stuff.
Now, some of these aqueous ions are measured a little different, so they may end up having negative values just to confuse things a little bit. So.
Should really get a binder.
Well, I can't speak any higher than these binders. I love these things.
Yes, I need to get one.
I used to have extra ones underneath here, but I'm not coming up with them now. I'll have to find it for you. I mean, it is in your book, and I gave you a PDF of the book, so it's on there as well. But at any rate, the entropy of these pure crystalline substances at absolute zero is zero, and there's only one possible microstate at that point. But as we increase the temperature, then those microstates increase and increase even more, and then increase even more. So like I said, as temperature increases, the entropy is going to increase as you move towards the melting point, and then a sharp increase at that melting point, and then an even sharper one here as we get rid of all of our intermolecular forces. Okay? So the absolute entropy of solids is less than that of liquids, less than that of gases, and a lot less. Absolute entropy of a small number of particles is less than a larger number of particles. That's where we're looking at moles of material. Okay? Absolute entropy of gases with smaller volumes is less than larger volumes because there's more room to spread out. There's more possibility for it being there, okay? You drop your earring in your car, all right, and try to find it. I know, you know, earring. Yep. and try to find it. It's going to be difficult, but not impossible. You drop that when you're out in the middle of Fayette on the football field, and you may as well forget it. Not going to find it ever. Okay.
I like to think of the drop it at your house versus drop it while you're away on vacation in Michigan or something.
Yeah.
Kind of thing.
But just bigger area even. It's hard to even find. And then it's going to increase with increasing temperatures because you've got more particles, they've got more speed, so they're more dispersed. All right, now this is where we need to be careful. This is that chart I was trying to get you to find, but we'll have to get you a copy, okay?
Wait, I feel like I just saw it. No, I didn't.
So when you're looking at your chart is going to have H in a circle, which is your enthalpy formations, and it's going to have S in one of this is called a prime. This 0 here is called prime, and that's going to be entropy of formations. Okay. The problem is, and they will do this on the AP exam, I swear up and down to you, they will. Okay, so be careful. These entropies are given in joules per mole Kelvin. Your enthalpies are given in kilojoules per mole Kelvin. So you have to convert one or the other. It doesn't matter which one you convert, but they have to be in the same thing. So be very, very careful, my young Padawans, because they will do it to you, I promise. All right, so predict the delta S, that's the change in entropy of the following. Is this going to have a positive or a negative entropy?
Which one, A or B?
A.
It's going to be a negative because it goes down in moles.
It goes down in moles, and you've taken a liquid and gone solid. Here, this one's going to be, well, they want to know sign, positive or negative? Positive. Okay. Which will have the greatest entropy? Metal at 273 Kelvin or the same metal at 400? 400, good. A soft metal like lead or diamond, which is a rigid solid? The metal will have greater enthalpy, okay? It's flexible, moving, okay? Two examples of the same gas at the same temperature, one with a pressure of 1 atm, one with a pressure of 0.5.
So 0.5 because it has more room for molecules to move. Is it in the same container with us?
Yeah, they don't state anything about the volume, do they?
I'm assuming it's in the same container.
Yeah, so this is less pressure. So this would be freer to move, I would suspect. Is my cheating stuff on there? What did I say on there?
0.5.
Okay. All right, good. Again, I got Cancun brain, so you should have seen me like it was 4th hour. I had some doozies there, let me tell you. It's just regular chemistry. It's not hard. I just screwed up a couple little things, like didn't put in the hundredths place in my calculator and came up with a slightly different, just very slightly, but just little things. Or I put down the molar mass instead of the answer to the problem for the blank. I mean, it was just silly little things, but luckily a couple of the kids knew what they were doing and they caught me, so that was good. All right, so the change in entropy in a reaction can be found by subtracting the sum of the absolute values of the entropy of the reactants from the absolute entropies of the products.
How do you find the steps?
You have to look at the enthalpy or the entropy values off of that chart that we need to find still. So, and again, the chart is in the online textbook. I will show you in a minute how to get to it. You're not going to have to do it today. You'll probably have to do some of it tomorrow. The thing is that when you look these up on that chart, and this is something you need to be very careful with, when you look those values up, you need, and I've screwed this up many times myself and not come up with the right answer. And I'm like, why am I not getting this? Like, I've got everything. No, you don't, dear. You do not have it right. Because I would look like for water, there's like two different ones. There's one for the liquid and there's one for the gas. And I was using the value for the wrong one. So be very careful that when you look on that chart, which I'll show you here how to get to, because this is what we're going to be working on tomorrow. When you look on that chart, that you're looking at the right phase. Okay. So let me just show you on here. Did I get attendance? No. Let me just show you real quick where to find that. So if you go here to classwork and you go important in resources, there is the textbook here. Eventually, there we go. And PDF.
Something pages.
Yep. But it's so much better than having to lug that thing from back to, home to here and back and forth. So it's not a perfect system, but it works better than the alternative. So come on. We're at the glossary now. Getting closer. Sped past the index. Oh, answers. Here we go. So here's your appendix C that we finally come to. So here's your delta H's that I was telling you about. And you do have some delta G's here, but they're for just one. These are all for one specific temperature. The temperature is at 298.15 Kelvin, which is what most of the problems are given at. So, but see here where this is kilojoules per mole. This is kilojoules per mole. This is joules per mole. And they'll get you. They will. And they fully intend to. So be very careful with that.
Oh, I feel like now
Here's where we're talking about water. It has gas here and it has liquid here. And I've screwed that up where I picked the wrong value because I wasn't paying attention to the state. Yeah, I gave you a copy of this. If you can't find it, let me know and I'll print a new copy for you. But that's what you want to look for is this appendix C. Okay, everybody cool? So I don't have any homework for you right now. I might find something, but I think you've got a pretty good grasp on the idea of increasing those microstates. So that's what I was looking for at the end of today.
Yeah, I just want to let you know before you do all my tests. I did not have my scientific calculator with me that day, and I kind of made do with one of the ones down there. So I'm guessing a lot of them are kind of in there because
Okay.
it was not easy at all.
Well,